Doug Finke, David Shaw, James Sanders, Shahin Khan, and I will be looking at the news in quantum tech globally, take a deep dive into a topic, and review progress on our predictions. This is the Analyst Roundtable.
I'm James Sanders with 451 Research, which is part of S&P Global Market Intelligence.
I'm Shahin Khan with OrionX.net.
I'm David Shaw with Fact-Based Insight.
I'm Doug Finke with the Quantum Computing Report.
Welcome, everybody, to the Quantum Analyst Roundtable, Season 1, Episode 6. Today we're one man short. David Shaw is out on travels, but we still have Doug Finke, James Sanders, and Shahin Khan, and myself to bring you analysis of the news and a little bit of a deep dive. James, Shahin, Doug, good to see you. Doug, you and I, we just got back from Boston, Quantum Tech. I know Shahin, James, or James, you are heading to HB Discover in a few days. Doug, you might be there as well. Anything through the grapevine that we maybe can start out with that hasn't made official news, but any impressions or findings that anyone might want to share before we get started?
Say a couple words about the Quantum Tech in Boston. It was pretty well attended. I think people are still very happy to be able to meet people in person, have drinks. The people just got tired of all these Zoom conferences, so it was good. And I certainly saw no let up in the excitement in the quantum industry in Boston.
What are you expecting at the HB Discover, James? Will there be quantum at all, or?
As part of the Cray legacy, and as you through that acquisition, I would expect that there's going to be a lot more HPC side of things, but the quantum story is a little bit an HPC one. If you're going to be doing a lot of scientific computing, where the inflection point is between a classical supercomputer and quantum computer is something that's going to be important to navigate. And while HPE is not building their own quantum computer, they definitely have an interest in that regard. So it'll be interesting to see where they're going with this emerging technology from there.
And we have go ahead, Shane.
The HPC market traditionally has also been an early adopter market. And because they have the scientific modeling and engineering modeling that is compute intensive, they end up actually having some of the valid use cases for these early technologies. We are seeing that in AI. They actually are emerging as a very important piece of the AI puzzle, both because HPC is needed to enable AI with all the algorithms that are needed, and also AI at the service of HPC. And the same thing is being seen in quantum computing as well. We talked about the Jülich Supercomputer Center in Germany, which I think is one of the leading places for hybrid quantum classical supercomputing, but also the big supercomputer centers in the US and the rest of the world. They're all over quantum computing. And of course, the PASI Supercomputer Center, we talked about that in pre-show, now has a tiny quantum computer as well. So it's happening there.
Good. Appreciate that little segue into the news. And let's go to the news. Start with a little bit of an investment overview. And Shahin, you asked the question earlier if investments are cooling down. Let's discuss that maybe a little bit. But since we last spoke, we had a $1.85 million round into our friends sitting out at the Brooklyn Navy Yard, König, by the Department of Energy to support their quantum repeater development and commercialization. Quantum Computing Inc., another little merger here, part of my thesis that we will get a lot of consolidation, acquired Q Photon. Quantware was awarded 7.5 million euros by the European Innovation Council to scale their superconducting quantum processor. And our friend from Paris, Christophe Jursac, and Quantum Nation hard at work with the Evolution Q and a $5.5 million Series A funding there, as well as a $16 million round into Qubit pharmaceutical. So actually seeing a number of deals here at definitely not the seed stage, but the A, maybe B stage, and less of the big SPAC or $50 to $100 million checks. Investments still hot or not? Any thoughts?
I think quantum computing continues to be an imperative, and that is really helping it. Everybody who is at the table recognizes that they need to be at the table. So I think while the price of money is going up a little bit, the availability of it for quantum computing and for it to be prioritized for quantum technology feels quite safe to me. However, as you mentioned, I also expect that the economic clouds might cause more acqui-hires, more mergers towards full stack, more motivation to really build the bench strength and the critical mass. So I do expect that sort of deals to happen a little bit more frequent.
Yeah, and one thing I would say is you need to differentiate a little bit between government investments and like venture capital investments. Governments do think long term. They will not let up on their investments just because the economies or the stock prices are down. They do see this as a national security issue, as a national economic health issue, and governments think on the long term. I think you may see a little bit of hesitancy, particularly on the venture capital side of things. The venture capitalists not only have to think about what they want to do, they have to think about what their limited partners want to do too. And some of these limited partners may get a little bit nervous just because all their other stocks and all their other portfolios are getting down. So there might be a little bit of more difficulty for companies to get private funding, but we'll have to see.
VCs with a background in deep tech, I think, are a little bit better at not looking at the world quarter to quarter or year to year. This is a definitely long-term investment, and even for private companies, there is too much of a if it's not heretical to say, there is too much of a focus on what are the improvements quarter to quarter when it's a marathon. It's not a sprint. As far as SPACs go, it seems that the garage door of the SPAC shack is closing, and there's maybe a couple of companies that want to get in just before it closes. But with the markets where they are, I think that's going to be, as hazardous, if not a little bit more than what the SPACs that have already exited to the public markets have experienced. That does seem a little bit perilous, but we'll see how that develops. I wouldn't expect a lot more in terms of new announcements of intentions to go public via SPAC, given current market conditions. But it will be interesting to see, and I think Andre's right. I think there's a decent chance for a bit more consolidation, especially where the market is right now. A lot of this game is going to be patents and talent. If you are going to try to start building up defensive patent portfolio, having an economic climate where there's a lot of people who need money or need an exit might be a little bit better for you than a healthier market. But I think a healthier market would be better for everyone in general, which is the least controversial thing I can possibly say.
In fact, Goldman Sachs, the leading Wall Street bank, just a few days ago announced that they will not be doing SPACs anymore. So that door, James, is closing very, very fast. The beginning of this year, I predicted a handful of more SPACs to happen. And now it looks like even a SPAC or two that already was in the works might not see the finish line anymore. So as Doug pointed out, there's still a lot of good and patient money out there, much of it from the government side. VCs and thinking of people like Quantum Nation and Christophe here do have highly experienced, highly dedicated funds that will not go away. Other VCs certainly might starting to feel the tingle in their toes and the cold creeping in. Let's move to the product and the tech side. I picked a few random, hopefully not too random, announcements here. One breakthrough, maybe we can explore this a little bit, was in quantum universal gates around high fidelity TOEFL gates. TOEFL are controlled CNOT gates that are the key to a logical gate, and it is at the Lawrence Berkeley National Laboratory that they were able to do this with 3 qubits. So really the ability here to scale your logic gates. Any thoughts on this? How long does it take for something like that to really be a breakthrough from the lab to what we discussed?
Well, one thing I would mention is, if you go to any of these quantum courses, they teach you sort of a standard set of gates, Hadamard gates, C-naught gates, X gate, Y gate, Z gate. But it turns out that in quantum, there are a lot of other gates that are out there. And in some cases, people will invent new gates. For example, I know that when it was at Quantum Tech, the Eleanor Rifle at NASA was mentioning that they were working with the Rigetti computer, and they came up with a different type of 2-qubit gate. So the advantage of doing this is that you can sometimes develop algorithms that have fewer gate levels by using these special gates that will do more than perhaps just what you could do with a standard set of gates. So we will see that quite a bit, I think. Particularly as people mess around at the pulse level to program the computer, using the pulses of the microwaves or the lasers, and it's all in an effort to come up with basically programs that can run in shorter number of gate levels and be more efficient.
So one way, I guess a simple way to understand these is that if you think of traditional computing, it is hinging a lot on the AND gate and the OR gate or the NAND gate. And these are logic gates that are very simple, and there's a finite number of them. And if you manage to do a very efficient NAND gate at the transistor level, then you can parlay that into operations that are more understandable: addition, subtraction, division, etc. And you keep building on that, and now you've got a digital computer. So for the quantum computer, those transformations are not NAND and AND gate. They are the CNOT gate and the Hadamard gate and these other gates. And these gates are fundamentally a shorthand to point to a transformation of input to output. And whether it's reversible or irreversible, these are all different kinds of capabilities. And just as that kind of digital transformation leads to arithmetic, the quantum transformations lead to the computations that a quantum computer can do, which is why quantum computers aren't good at additions and subtractions, but they are good at doing the Hamiltonian of this or that or the other. So I think if you think of it that way, and if you think that the universe of transformations for a quantum computer is not so limited as a 2-bit logical thing, then you sort of open up the possibilities. And people can think of new things, and new materials can enable new things. Some quantum computers are better at this particular transformation than that other transformation. So when you compile your code, you want to preferentially treat that transformation than not. That may, and this is, I think, why the multimodal thing is a concept, is that you may have a quantum computer that's good at this, but not good at that.
Something even more futuristic announced a couple weeks ago. And I remember somebody on stage in Boston last week exclaiming, "Please give us a QRAM. It's the only thing that is missing." The future of quantum RAMs, scientists announced that they observed the interaction of 2 time crystals. And unlike a Josephus junction on a qubit that exchanges information in spatial dimensions, time crystal replaced that spatial dimension with a time dimension. Time crystals were first grown, I believe, about 6 years ago, so very, very recent. And now for the first time, researchers were able to observe an interaction between two time crystals. Extremely futuristic, but hailed as the future of QRAMs already today.
Well, we already have sort of a semantic problem in quantum computing because we use qubit for processing as well as storage, because bit in the compute, in the traditional computing, a bit is where you store stuff. It's not where you process stuff. Whereas in a, you take it to a CPU and that's where the processing happens. Whereas in the quantum computing, you almost have a merger of storage and processing, and the more qubits you've got, the more powerful you are. So QRAM is semantically a little bit different, is that, oh, it's just for storage. And I think its creation will be critical. I think it is a big piece to try to open that up and to allow quantum computers to actually have data that they can access at will. Because I think, as we discussed also earlier, putting data into and out of anything is hard, and it is especially hard for quantum computing.
Yeah, the other thing I would point out is it's not only quantum computing, it's quantum communication. The big limiter right now to having these very long fiber optic cables is the fact that there's loss in the fiber optic cables, and you need to put together a quantum repeater in order to repeat the signal, which is a little bit tricky because of the fact that you can't clone a qubit. But there are fancy ways of doing it, something called entanglement swapping. But in a quantum repeater, something called a quantum memory is a critical function in order to synchronize the various photons that are coming together. So I actually think that will be a very big market eventually for various types of quantum memories is in these quantum networks.
And I'm curious to see who will jump on the next one first. Tony Utley made that announcement also in Boston. Quantinuum and the new, or rather still the old H1 machine in a new iteration broke a new performance record with 20 qubits. I thought we were at the 256 qubits by now in the competition. Why would they announce 20 qubits?
I guess the thing to point out is that the way that an ion trap system is manufactured is going to be a lot different from the higher qubit counts that you'd see in a superconducting system. If I remember correctly, the H1 is still very much the 1D, the linear trap system. It'll be really interesting to see, what the launch of H2 and a somewhat different topology for how they're, putting all this stuff together, and what kind of performance increase you get from that. But this is another milestone in Honeywell is sticking to the roadmap that they had plotted out. I think that was just before COVID hit. So it's always nice to see, any company delivering on the roadmap that they've set out. Especially, I don't think any of us deal a whole lot with a lot of quantum naysayers, but there are still a few out there. So being able to point to, promises made, promises delivered is always a good thing.
Yeah, the other thing I should point out is Quantinuum has one of the highest qubit qualities, the best qubit qualities in the industry. So you just can't look at the raw qubit counts. You have to really look at the qubit count plus the qubit fidelities. And, they had announced, maybe a month ago that they had hit a quantum volume of 4096, which is the maximum you can go with 12 qubits. So now that they have 20 qubits, and they made a point to say that they did not decrease their quality levels when they went from 12 to 20, they may disclose some new records eventually on even higher quantum volume numbers.
Yeah, I thought that's really their fidelity being the champion again, and that's wonderful. I basically think that you look at the DiVincenzo criteria and you just go down the list, and whatever your strength is going to manifest itself to the metric that includes it. So if you're doing quantum volume, then fidelity is a big deal. If you're doing clocks, then maybe one more thing is a big deal. But at the end, you're going to need all of the above until you get to sufficiently big circuits with some, yeah.
And
I'm also glad that Honeywell is pointing out that, this is a 20-qubit machine and being upfront with that number. And we had talked about this a little bit in the pre-recording session, but being upfront with where you are in technology today is kind of important to, develop these roadmaps and show progress over time. If you try to obfuscate, and yes, in the let's say comparison of their superconducting vendor with triple-digit qubit counts, and we're shipping something with single-digit qubit counts, that's maybe a comparison that understandably you would not precisely want to invite, but not every qubit is built the same, and the meanings of these things are so abstract that with all of the benchmarking out there, there's still a tendency to want to use qubits as a heuristic for absolute performance or compute ability, and it's just not that thing. So it is nice that Honeywell was very upfront with the number of qubits that they're using in this latest announcement.
And Tony Utley from Quantinuum made this very clear. Their goal is not to have the most qubits possible, but get the most performance out of each qubit, and they have absolutely done that, and not to benchmark their own performance, but let customers do that. In this case, Mark Pistaya and his team at the JP Morgan that published a benchmark paper on the new H1/2 machine with the best-in-class performance out there in the market. The execution on the roadmap and the transparency is indeed laudable. Chicago expanded and activated its quantum network, adding a second link. I don't remember exactly to what length it now brings us, 124 miles. Going all the way from Batavia, Illinois, via Argonne National Lab to the Hyde Park campus of the University of Chicago, building so far the largest US-based network.
I think Brookhaven had another one a few months ago that went just most of the length of Long Island. So those are really nice to see, and a great breakthrough. I thought that was a significant news this past month.
And you'll see further expansions too, because remember in the Midwest they have the Chicago Quantum Exchange, which has other universities in downstate Illinois and Wisconsin. And I wouldn't be surprised sometime in the future they might extend networks to some of those other places.
Now, this one was together with Toshiba, which
Yes.
obviously is one of the leaders here. Yes.
And I would expect more quantum networks in the US to be announced later this year. I'm not sure if we had covered this on one of the past episodes, but there is an initiative in Singapore to develop a quantum network as well. And I believe that work on that is ongoing at a reasonably rapid pace as well. So it's interesting to see the number of quantum networking initiatives that are happening, even with quantum computing being still relatively early stage. But if you look at the history of classical computing and classical networking, this is the time to do it.
And a big driver for this is really quantum communication, as you mentioned, Doug, before in the other thread, as well as quantum safe post-quantum security. So I'm seeing a lot of activity in post-quantum security that's driving new methods of guarding information, especially in the times that we live in. So I expect that to continue to be a really big driver for all of this.
Staying in Japan, Shahin, you mentioned Toshiba's role in this. Taking a look at Fujitsu, a name that we don't see all that much in the news, that we nonetheless know well. Nature magazine published, and I haven't seen a ranking, I need to look it up, but they ranked all the machines out there by their ability to solve NP-hard problems. And Fujitsu Annealer came out first against everybody else and in front of our friends at D-Wave. And the Shiba simulated bifurcation machine. How do we place this type of announcement? Nature is a very credible source, of course. I don't know if any of you has seen that paper.
Fujitsu is a technology powerhouse, of course, and they had the #1 supercomputer in the world until a few weeks ago, when the system at Oak Ridge National Labs exceeded it by quite a bit, by like a factor of 2 to 3. But Fugaku, which was the #1 supercomputer until then, is a Fujitsu machine. It's a physically gorgeous machine, an architecturally beautiful machine, and it was a pretty big help in the COVID and the search for solutions for COVID. So it's a very significant system, and it demonstrates what Fujitsu can do. They've had a digital annealer chip for a few years now that is in fact a good segue into another emerging market to do these quantum computations in a classical world, and they have optimized silicon to do the annealing process in silicon, and it makes some things a lot easier, and you're seeing the results.
One thing I would add is I do tell people that the classical world is not standing still. There's some people take a simplistic view. They're saying Moore's law is slowing down, and we got to move to quantum because it's the only way to continue performance improvements. And that's not exactly true. There's still a lot of innovation happening in algorithms and in architectures and non-von Neumann architectures that classical computers are still being improved, quite rapidly. So, when we talk about quantum advantage, I'd point out that it's a constantly raising bar. What might achieve quantum advantage in 2022 may be achievable with a classic machine in 2023 or 2024. So, for a CIO out there who's trying to look at a hard problem in their business, I would say don't ignore a classical solution. If you might be able to find a classical solution that can still beat out quantum.
In terms of both hardware and software, to your point, Doug, there's a lot of enterprises that are really not at the state of the art. So there's a lot of gap. Well, maybe not a lot of gap, but there's a sufficient amount of gap that you can do a lot of upgrades to, your classical compute stack and the software and algorithms that are running on it to squeeze out more performance than what's being found today. Software optimizations are never the most fun thing to do, but it's important work and can really squeeze out, like I said, more performance. It is interesting to see the expansion of quantum computing beyond just computing, especially in the last year, in terms of media coverage, in terms of public understanding, the amount of, we're getting away from just gate model, especially with not just D-Wave, but also Fujitsu's annealer. And before our previous topic of quantum networking, there is so much more to quantum than just computing, that the fact that this is getting more investment and more attention is rising tide lifts all boats, right?
Back to quantum computing for a minute, because I think we're seeing a little bit of a sea change here that frankly might go unnoticed. Last episode, we talked about IBM's quantum volume record and roadmap for interconnected quantum computers. So that is superconducting. We shared the news from Continuum and their new benchmarks in a trapped ion modality, setting new records. Just discussed how an annealing architecture is extremely competitive in very specific problem areas, and an announcement from 10 days ago by the Ministry of Defense buying their first quantum computer, and it's a photonic quantum computer.
The Orca system. I thought that was also a very significant piece of news, and we now have photonics quantum computers in the US with PsiQuantum, in Canada with Xanadu, and now in the UK with Orca. I love the picture that they shared, because if you notice, it says 25 degrees Celsius. So it's very much room temperature, and it's a rack mountable device. The one at Pawsey is a different model, but that also was a small pizza box looking thing. So I like that these quantum computers are now coming in a form factor that is a little bit easier to accommodate in a data center, or even in the Pawsey case, it looks like it's sitting on a desk. So that's very important.
Unfortunately, we don't have a lot of technical or performance specs on this machine. If the Ministry of Defense buys this, we can only hope that it is able to do something useful. But this is a big announcement for photonics, no?
I think so. And of course, the promise of photonics has always been room temperature operation that makes a giant difference in total cost of ownership and operational complexity. So if this pans out as they hope for it to do, of course, it will be very, very important.
Yeah, I think you should remember that one of the purposes of both of these things, the Quantum Brilliance Pawsey thing and the ORCA Ministry of Defense, is really to investigate how you can interface a quantum computer to a classical computer. You know, that is non-trivial. It does take a lot of work, particularly to get the most out of it, how the two interact. And I think both of those systems are a relatively small number of qubits, but the things that they will learn about integrating classical and quantum, I think, will be very, very helpful.
And to round out that picture, an announcement by our French friends, Pascal, with two 100 qubit machines to go support the pan-European HPC efforts. And of course, Pascal uses the neutral atoms modality. So now all of a sudden, and that was not the case just a few months ago, we have superconducting, annealing, trapped ions, diamonds, and photonics and neutral atoms in market being commercially deployed. To me, this is we used to have one option and then some trapped ions. Now everything is being validated and rolled out in the market.
So I think this is a phase shift. I think this is a phase shift for the industry, where we now actually have several horses in the race. And I'd like to think that this is pushing us towards the clarity that the industry needs to know whether it's stuck with multimodal systems, or is there going to be a winner, as I've referred to, you know, whether we have the, you know, VHH Betamax, or whether it's our transistor moment, or some other analogy that suddenly creates enough clarity to say that, okay, we're going to like invest on this for the next 10 years. And so I just feel that it's a very important phase shift in the industry.
This is enterprise compute in the 90s all over again. This is the era of, you've got, you know, 7 different architectures, you know, power, alpha, MIPS, all of these things. But the event horizon for how long these are going to be in market, I really think is going to be a lot longer than that blip in the 90s where everyone had their own architecture. This could be a decades-long thing of, you know, maybe there's a workload, let's say pharma might work better on, you know, one modality over another. And until we get to, you know, 6, 7-digit qubit counts of fully connected, error-corrected systems, which is going to be a while off, I really think we're going to see these modalities coexist for quite a while. The question is, you know, what level of consolidation is there going to be between efforts? There's a lot of companies, a lot of very well-funded organizations that are pursuing superconducting quantum, you know, superconducting qubits. At what point do those efforts need to be consolidated? So it'll be interesting to see, you know, if there's a pivot for the brands familiar to millions in pursuing just superconducting, or if they're going to go with another modality in parallel. But this is, it's enterprise in the 90s. It's everyone's got their own architecture.
But you know, the analogy with computing is pre-transistor. We're talking Babbage machine. We're not quite there yet when you look at Bunch and say Burroughs Univac, you know, etc. So I think we still have ways to go before we get to even the enterprise.
Yeah, but this is endemic with all new technology. I mean, even in the early 1900s, with early automobiles, you had steam automobiles, battery electric automobiles, and gasoline powered automobiles fighting it out. And for a long time, of course, gasoline was winning out. Although there are diesel also, and even people were experimenting with turbine automobiles. And batteries are now coming back. So you see this overall. The other analogy I would use is the semiconductor industry, between gallium arsenide and silicon bipolar, NMOS, CMOS. So this is very, very normal for any type of new technology.
We also are going to talk about another architecture is not the right word, but the quantum simulation, which also plays a very, very strong role, at least in certain niches when it comes to simulate quantum mechanics for certain difficult computational problems. And there are different approaches on how to do that. Can we quickly just kind of explore the two main approaches to quantum simulation and where that stands out?
Okay. Well, quantum simulation can have two different meanings. The first is to use classically based technologies to simulate quantum. We have a simulation box from Atos in France that can simulate the quantum. We have the NVIDIA. They're using GPUs in order to simulate quantum. There's a number of different types of simulators at Amazon and Microsoft, again, that use their classical computers to simulate quantum phenomena. So, those are certainly very helpful for teaching quantum and people to at least develop their POCs. The one big advantage I would say about using those is that you don't have to worry about qubit fidelity. You can assume that a classical simulation can provide you 100% qubit fidelity. So if you're just concentrating on your algorithm, maybe you don't want to worry about errors initially. But there's a second meaning for quantum simulation, which is to use a quantum computer to simulate a quantum chemical reaction. Because when two molecules come to some type of chemical reaction, it's all governed by quantum phenomena. So when you talk about quantum simulation, you sort of have to define which one you need. Both, of course, are very valuable.
And we're seeing the word emulator also show up, not exactly in its kind of intended meaning, but to try to distinguish between those two different types of simulations. But in general, we see this emerging as its own market segment, that these simulators are not just a stopgap to use while you're waiting for the quantum computer to come, but they may very well be a destination in themselves. That if you're putting a lot of effort into developing these quantum algorithms, you're going to want to run them somewhere. And if the quantum computers are proving elusive, maybe you can run it on classical systems with GPUs or the digital annealer or FPGAs or other kinds of accelerators that might get you home in a good way. And you get, so you're getting the return out of that investment sooner than you otherwise would, while you track the development of actual quantum computers. So this kind of emulator simulator market segment now sits in between classical computers and quantum computers and may just provide a easier path for customers to get return out of investment. So that really is significant in my mind.
There is a lot of value in this in terms of it's a new way of thinking about some technologies that are already accessible. One thing to kind of key in on is it's really interesting to see, and this is classical, but NVIDIA's CUDA stack for its GPUs has really, really been responsible for a lot of the advancements in GPU. Any scientific workload, not necessarily graphical, that you want to run on a GPU for that performance enhancement. And when you compare the maturity of the software stack in CUDA to things you can use with AMD GPUs, there is a bit of a difference. And AMD's had its own trajectory, and they have to focus on kind of a core business, especially when these decisions were being made 6-7 years ago. But the importance of the software side of this story in terms of simulation is really in the idea that you have to develop the software in tandem with the development of quantum hardware. And I'm going to get back on my 90s compute thing again. There's a really good example of not doing that and it not going particularly well for anyone, which is Itanium. If you look at the development of Itanium, the idea is that we'll build this really great silicon, which is a really different way of building a classical CPU from what came before it. And once we've got that set, we'll start working on the compilers. And development of the compilers for Itanium were always a little bit later on, always a little bit slower than the silicon that the hardware developed. And the compilers never really matured in a way that gave Itanium a higher level of performance than x86 or x86-64 that came after it. And so it is really important that you develop and prove out these ideas for how do you write and run software on quantum computers before the hardware is available, because you really don't want any modality of quantum computer to wind up like Itanium did.
All right, even without our British friend David Shaw, who is still recovering from celebrating the Queen's 70th anniversary, we managed to get overtime. Quantum is too exciting and maybe a sea change. Many different architectures and modality finally being rolled out. One final mention, PsiQuantum announced their Q climate with a Q, unpronounceable, but very, very important. It is not all about business use cases, but the bigger good for humanity as well. Long live the Queen. This concludes Season 1, Episode 6 of the Quantum Analyst Roundtable. Round and round we go. Round and round we go. You can find each individual analyst's research and analysis online at quantumworlddetangled.com. We hope to see you soon. This concludes the Analyst Roundtable. Quantum is coming.